Hey guys, here's the clickers for chapter 7. Once again, I'll go through them fairly quickly, so pause the video when you see the question to give yourself time to think about it, and then resume to see the answer, and I'll give short explanations if it's necessary. All right, so here we go. First one, let's do it this way. There we go. There we are. Okay, ball rolls around a circular track with an angular velocity of 4 pi radians per second. They want to know the period of the motion. Remember, the period is the time that it takes to go around one full time. Okay? Now, the hint on this one, if you need it, is to remember that there are 2 pi radians in one rotation, and then go through it as a conversion factor. Here's the answer. Half a second. So again, 2 pi radians per revolution and 4 pi radians per second. So that means 2 revolutions per second or half a second per revolution. Next one, we have Rashid and Sophia on a merry-go-round. Sophia is twice as far out from the center as Rashid, and we want to know to compare their angular velocity. Here's the answer. It's the same because they're going around in the same amount of time. Now, it's true that Sophia is covering more ground and her tangential velocity is greater, but the rotational velocity, like the speed of a second hand on a clock, is the same for both of them. They take the same amount of time to go all the way around. Okay, how about their speed? And I did say that Sophia is faster, but here's the answer. Sophia's speed is twice as much as Rashid because her radius is twice as far as Rashid. And here's that very handy equation, V equals omega r, where there's also one for acceleration, A equals alpha r, and one for displacement, D, distance, equals theta r, where as long as you keep it in radians, works great. Next one, 2 coins on a turntable. Coin B is twice as far from the axis as coin A. Compare the angular velocities. Here's the answer. They are also the same because they both go around in the same amount of time. This is the same situation as the Sophia and Rashid question. Next one. Here's a propeller. Let me move my smiling face out of the way there a little bit. Okay. Want to know the signs of omega and alpha. Here's the answer. How about this one? There's the answer. Okay. And really what they're all asking about you here is the conventions that we use for positive and negative. So clockwise is negative by the normal convention, and counterclockwise is positive. So the rotational velocity, the direction it's turning, is clockwise, which means it's negative. That's the negative. But it's slowing down. So the acceleration is in the counterclockwise direction, so that is a positive acceleration. Okay, and here's the next one. Same situation, only this time the blades are speeding up. So here's the answer. They're both negative because both the rotational velocity and the acceleration are in the clockwise direction, so that's negative by convention. Next one. All right, we haven't seen one like this in a while, but see if you can figure it out. It's a rotational velocity versus time curve, a V versus T curve. And they're asking you how many revolutions that it makes. Okay, here's the answer. It's just the area under this curve. You may remember this, that displacement is the area under the curve. So in this case, each square represents 1 revolution, because if you do base times the height, you get revolutions per second times second, meaning use just with revolutions. So each square counts as 1 revolution. So 1, 2, 3, 4, 5, 5.5, 6. Now, if this was radians per second, then each square would represent a radian, but they happen to do it in revolutions in this one, so there you are. Next one. Okay, starting from rest, wheel with constant angular acceleration spins up. We want to know its angular velocity after time 2t. And here we go. This is the answer. 50 RPM. So they're assuming constant acceleration here. So it gets up to 25 RPM in a certain amount of time. Well, in twice the amount of time, it's going to be going twice as fast. So 50 RPM. Next one's a little more tricky. Here it is. We want to know in this one what angle in radians it has gone through after time 2t. Okay, so definitely pause this one and think about it. I'll give you a hint here in a second before I go over. Okay, here's the hint. The hint is to use the equation d distance is equal to 1/2 at squared, which on the AP gouge is part of the really long one with x final is next naught plus v naught t plus 1/2 at squared, that thing. We're only using the acceleration term in it, okay? Now, it works the same way in rotation, so in that case, it's going to be theta, the displacement, is equal to 1/2 alpha, which is the angular acceleration, times t squared, all right? And then compare one time period versus 2 time periods with the same acceleration. They don't give you the acceleration, but the implication here is that the acceleration is the same in both places. So anyway, here's the answer. And it does come out to be 100 radians. Their explanation here, I think, is not really complete, but if you can make sense of it from that, good on you. Working the problem and doing the calculation is probably a better way to go here. All right, moving on to the next one. Finally, a simple torque question. We want to know which force is going to have the most effect on opening the door. Here comes the answer right about now. There it is, force A. This one down here gives you the most leverage, if you want to think of it that way. Really what it does is it produces the most torque because you have a force which is farthest from the hinge, so gives you the most torque. Okay. We want to know which one of these forces applied to point P will make the net torque 0 and put the thing in equilibrium. Slide down here just a little bit more. And here comes the answer. There it is, that one. So twice the magnitude of force, and it is working perpendicular to the moment arm for that point. So here we have a relatively small force going to the right. This one we need double the force going straight up because its lever arm is only half as far. It's only half as far from the pivot point. So that's why it is. This long one here does not produce any torque whatsoever, so we can ignore it because the question is only asking about torque. And here we go. Where the center of gravity of the L-shaped piece be? Make your best estimate. Here's the answer. There it is. And that's all we have. Okay, we'll go back to that one. So I'm going to close this one down, bring up the ones from Chapter 8. It's just a very short thing, so it will only take a moment here. So bear with me while I bring this one up, and it will be this. Right, and let's do the slideshow. And current slide, and here we go. Okay. Which object is in static equilibrium? So you might want to pause this one. Remember, static equilibrium is when the linear forces are in balance and the rotational forces, the torques, are also in balance. Okay? And here we come to the answer. And it is D. Now, why is it D? Okay, for linear forces, we have two small forces going to the right and one big force balancing it to the left. The magnitude of this one is twice the ones to the right. This one doesn't do it because we have the same magnitude force going to the left as twice going to the right. Okay, now rotationally, this one does not work because this force is not aligned with the center of mass, so it's going to produce a torque and it's going to cause this thing to start spinning counterclockwise. This one, everything balances out. Now, this force by itself will cause it to torque it clockwise, but this one is the same force torquing it in the opposite direction. So these two will cancel each other out. This provides no torque because it's lined up with the center of mass of the object, so that's why it's D. Okay, next one. What does the scale read? Let you figure it out. And as I say, it requires reasoning, not calculating. And the answer here is 2,000 newtons. So we have 1,000 newtons pulling downward at a long distance from the hinge. So our rules of torque tell us that it's got to be twice the force if it's acting at half the distance, which it is. So it's going to be 2,000 newtons. And you can use math for that one if you want. Calculating will work fine. And that's it. So anyway, hope that was helpful.